everyone. In this video, we're going to continue our discussion in chemistry by talking about chemical reactions. In order to discuss chemical reactions, we first need to consider chemical notation, which basically is a series of rules that allows us to understand how we write out elements and molecules and components of the chemical reactions. So if we simply write the symbol of an element, that means that we're representing one atom of that particular element. So for example, if we write an H, we mean to say one atom of hydrogen, or if we write an O, we mean to say one atom of oxygen. Second, when we write a number in front of the element, that means that we are representing more than one atom. So if we write 2H, that means 2 atoms of hydrogen, or 3O, that means 3 atoms of oxygen. Chemical symbols that are written with subscripts imply molecules that have that particular number of atoms in that element. So if we write H2, that means that we have 2 H's that contribute to the molecule. If we write O2, 2 atoms of oxygen contribute to the molecule of oxygen. If we write H2O, that means that there are 2 H's and only 1 O. So if there's no subscript in front of the particular symbol for the element, that means that will imply a number 1. So the number 1 is assumed when there's no number written. If there's a superscript, like a positive or a negative, representing a charge, that means that it's an ion. So if we write Ca by itself, we would mean 1 atom of calcium. But if we write Ca2+, that means that the calcium has lost 2 electrons and now it's a calcium ion. Similarly, if we write Na with no charge, then we mean sodium the atom. And if we write Na+, we represent sodium the ion because we've lost 1 electron. Participants in a chemical reaction are called reactants and products. So if we write 2H plus O with an arrow pointing to H2O, we will use the arrow to identify the direction of the reaction, and whichever way the arrow is pointing, the tail of the arrow is going to be towards the reactants, so the 2H and the O are the reactants, and then the head of the arrow, the direction it's facing, is going to face towards the products, and so we're making H2O. Now, if conversely we see 2 arrows, one arrow pointing in one direction and then another arrow pointing in the opposite direction, that implies that the reaction will proceed in both directions. So not all reactions are reversible, not all reactions can proceed in either direction, but some reactions can, and those reactions will be represented by the double arrow. Now, of note, chemical reactions can't create or destroy any atoms, so they simply rearrange. A reaction has to be balanced. We have to start with the same number of atoms of each element in the reactants and end with that number in the products. So for example, when we consider 2H plus O equals H2O, we notice that we have 2 H's in the reactant side of the reaction and 2 H's on the product side of the reaction, and then similarly 1 O on the reactant side and 1 O on the product side. Next, let's talk a little bit about chemical reactions. So chemical reactions create new chemical bonds between atoms, or they break existing bonds between atoms. And sometimes it'll be a combination of both in the same reaction. Metabolism refers to all the chemical reactions occurring in the body. At any given time, this will be a combination of forming new chemical bonds and breaking others. Work is the movement of an object or the change in the physical structure of matter. Work includes things like walking, running, synthesis of organic molecules, conversion of vapor to water. The examples really are endless, but it's important to note that work is required in order to have chemical reactions. Energy is the capacity to perform work. So movement, any type of physical change really, cannot occur without energy. There are 2 types of energy that are important to consider. Kinetic energy is the energy of motion. It's basically energy that is doing work. And potential energy is stored energy. So it's energy with the potential to do work. Oftentimes, heat will be released as a product of doing work. Energy cannot be created or destroyed, but it can be converted to something like heat and then not be recaptured. So we can lose energy in a chemical reaction. Work is the conversion of potential energy to kinetic energy via chemical reactions. So there are approximately 5 types of chemical reactions that we like to consider, and some of these terms can be interchanged for other terms that essentially mean the same thing. So the first type of reaction that we want to mention is decomposition, which basically means that molecules will be broken apart. So we start with AB as a molecule and we break it into elements A and B. The next reaction type we'd like to consider is synthesis, which basically is assembly of larger molecules from smaller ones or formation of new chemical bonds. So we could start with elements A and B and then make product AB or molecule AB. Synthesis reactions are alternatively called combination reactions. The next type of reaction that we like to consider is the exchange reaction, which involves both decomposition and synthesis. There are a couple of different types of exchange reactions. The first type is single displacement. Single displacement means we're going to replace one atom or ion of a particular compound with another atom or ion that initially is separate. So, for example, AB plus C makes AC plus B. We also have double displacement, in which atoms from different molecules or compounds are swapped around in the reaction. So, for example, AB plus CD makes AC plus BD. A reversible reaction, as we mentioned before, is a reaction that can occur in either direction. So a reversible reaction will be characterized by the double arrow, and the reaction going in one direction is, so for example, a decomposition reaction, and the reaction going the opposite direction is a synthesis reaction, or we could have an exchange reaction that could proceed in either direction as well. Finally, equilibrium reactions are opposing reactions that occur simultaneously. So let's consider the reversible reaction above. A plus B makes AB molecule, and then the reverse, AB molecule decomposes into A and B elements. And let's think about this in the context of equilibrium. So let's say that initially we have in a pool, all in the same place, so they have access to each other, 20 A's and 20 B's and only 10 AB molecules. So there are more A's and B's than there are AB molecules, and the reaction is looking to balance itself over time. So initially, the A's and the B's in elemental form are going to combine to make the AB molecules at a much faster rate than the rate at which the AB molecule is going to decompose into the A and the B in elemental form. So we want to go from having 20 A and 20 B elements respectively and only 10 AB molecules to having a nice balance of 15 A's, 15 B's, and 15 AB molecules. So if we proceed in the direction of synthesis faster than the rate of decomposition, then we'll get to a point where we do have that balance of 15, 15, and 15 across the board. Once we get to that place of balance, the rate of synthesis will equal the rate of decomposition. That's what's meant by equilibrium. So we now have a balance between the reactants and the products, and subsequently a balance in the rate of synthesis and decomposition. This principle is Le Chatelier's principle. Basically means that we want to stabilize the concentrations of the products and reactants over time. If suddenly, once we have our stable environment, or even before that, we were to suddenly add a whole bunch of A's into the pool, now we've disrupted the chemical equilibrium. And because we've disrupted the chemical equilibrium, the rate of synthesis now is going to increase with respect to the rate of decomposition, because now the reaction wants to balance out all those A's. So the reaction again will become unbalanced until it is able to even out the products and the reactants, and then eventually we'll be back to our state of equilibrium. The process of equilibrium is very dynamic. It's able to adjust to ever-changing circumstances, ever-changing availability of reactants or products. It's super critical in the human body because this is one of the ways in which the body will maintain homeostasis, by utilizing Le Chatelier's principle to maintain chemical equilibrium in a variety of reactions that occur on a minute-to-minute basis. One thing that's important to consider in terms of chemical reactions is activation energy. So activation energy is the energy that's required to start a reaction. And chemical reactions may be activated by things like temperature, pH, a hostile environment, or a lot of energy. But sometimes the amount of energy that's required makes the reaction a little bit unrealistic. It would take too long to get up enough energy to start the reaction. So we can utilize things like enzymes. Enzymes are generally they're proteins in terms of their chemical construction, and they have the ability to lower the activation energy, which means that they can accelerate the rate of reaction. Now, enzymes are not consumed in the reaction, and they can't change the products or the direction of the reaction, so there are some clear limitations, but they can increase the rate of the reaction by lowering the activation energy, so they're extremely useful. And there's a significant abundance of enzymes in the human body. Now, if we were to write the chemical reaction if we were to write the chemical reaction so that we could represent the use of the enzyme, we would write the enzyme over the arrow. So A plus B, arrow AB is simply a synthesis reaction. But when we write the enzyme, we would write the actual name of the enzyme, not the word enzyme, over the arrow. It's telling us that an enzyme is being utilized for the purpose of activating this particular reaction. So we're doing a little cartoon drawing real quick. So an enzyme can take many shapes, and there are a couple of different theories about how enzymes work, and I'm going to address both of them briefly. So enzymes interact with substrates, and substrates are nothing more than the reactants. When the reactants are interacting with when the reactants are interacting with an enzyme, we change the name of the reactants to substrates. And enzymes oftentimes will have an active site, which is a particular place where the enzymes have to contact the substrate in order to catalyze the reaction. So there are generally two different ideas about how enzymes work. One is the lock and key model, which basically means that there's a right fit for the substrate into the enzyme. And because it's a right fit, the substrate is able to bind to the enzyme. And in this case, we're showing two substrates that we want to combine, just like we drew in the original reaction with the arrow. And so the A and the B are going to bind to the enzyme, and then the enzyme is going to catalyze the formation of the AB molecule. And then afterward, the AB will be released from the enzyme, and now it's its own molecule. It's the product, and the enzyme remains intact. The other model is called the induced fit model, which is a little bit different. The enzyme is not in the shape that it needs to be in when the substrates arrive, but the arrival of the substrates and the contact of the substrates to the enzyme will cause the enzyme to change its shape slightly. We'd call that a conformational change. So change its shape slightly to accommodate those substrates and then catalyze the reaction. The induced fit model is the more widely accepted model for enzymatic function. So enzymes are very specific. There's many different enzymes that are needed to catalyze the different reactions, because a particular enzyme will typically only catalyze one reaction or one type of reaction. Now, the rate of the reaction is limited by the availability of the substrate and the availability of the enzyme. So we can only increase the rate of the reaction as fast as there are enough enzymes to keep the reaction going. All right, so let's take a look at some examples. So let's consider this little person who is having a pizza and beer night, and then perhaps the combination of those things in excess is leading to an increase in acid production in the stomach, which is going to make him feel pretty unhappy later on and will result in the need for taking Tums. So taking Tums actually is going to cause chemical reaction in the stomach, and we're going to write it out so that we could take a look at it. So we see CaCO3, which is calcium carbonate, which is Tums, combined with hydrochloric acid, which is stomach acid, to make three new products. One of them is calcium chloride, which is like the chalky substance that is the byproduct, and then also water, and then carbon dioxide. So Tums actually causes some fizzing when it's in the acid, and the fizzing is actually the CO2 being released as part of the chemical reaction. So I just want to use this as an example so that we can take a look at the different elements that are contributing to the molecules and the compounds here, as well as to show that a chemical reaction is nothing more than a rearrangement of a bunch of different elements that were originally stuck together in one way and can be stuck together in a different way after the reaction is over. So we're not going to worry about exactly how this reaction is happening. Reactions really are mostly about electron transfer. So we're going to kind of skip that piece of it and just take a look at the letters on the page. So on the left, we see 1 calcium. On the right, we see 1 calcium. On the left, 2 H's. On the right, 2 H's. On the left, 1 carbon. Right, 1 carbon. Left, 2 chlorides. Right, 2 chlorides. Left, 3 oxygens. And right, 1 oxygen and then 2 oxygens, making 3 oxygens total. So this is just a perfect example of showing that the chemical reaction is balanced. We have the same number of atoms of each element on either side of the reaction, the side with the reactants and the side with the products. Let's consider one more. This reaction is going to be a reversible reaction that actually occurs in multiple stages. So we'll start with H+, which is a hydrogen ion, and we'll combine that with HCO3-, which is bicarbonate ion, and those will form H2CO3, which is carbonic acid, and then carbonic acid will degenerate into water and carbon dioxide. Now you notice that this reaction is reversible, so everything that we just described in the forward direction could also occur in the reverse direction. H2O and CO2 combine to form carbonic acid, which dissociates into a hydrogen ion and a bicarbonate ion. So this reaction is called the carbonic acid bicarbonate buffer system. Not today, but soon. This reaction must be committed to memory because this chemical reaction is one of the major contributors to equilibrium in the blood, and it's necessary for maintenance of homeostasis. So let's just we'll sort of repeat our process here and compare the different atoms of elements in each piece of the reaction. So starting from the very left in blue, we have 2 H's as the initial reactants. When we form the carbonic acid, we have 2 H's, and then when we dissociate into water and carbon dioxide, we have 2 H's. We have 1 carbon initially in the bicarbonate ion, 1 carbon remains in the carbonic acid, and 1 carbon transitions to carbon dioxide at the very end. And then lastly, 3 oxygens making up the bicarb, 3 oxygens found in carbonic acid, and then 1 oxygen in water, 2 oxygens in carbon dioxide, making a total of 3 oxygens in the final products. So once more, all we're doing is rearranging the letters, rearranging the atoms of the elements so that we can make different molecules, different compounds that essentially perform different functions at different times in the human body. So other than the fact that eventually this particular chemical reaction must be committed to memory, the big picture here is really what's important. And the big picture is that if we can take these different elements and stick them together to make molecules, and if we can then take those molecules and rearrange them to make new molecules, that is super critical to how the body will function on a day-to-day, minute-to-minute basis. It's also how we'll start to show that we can build larger structures from these tiny little elements, and that's really kind of why we spend this time with chemistry while studying anatomy and physiology. So focus on the big picture, and we're gonna kind of keep it moving. Next up, we're gonna talk about inorganic compounds. So I hope you enjoyed this video. Thanks for watching.